Okay, so we're now going to look at forced oscillations where we apply a force that's periodic with the frequency omega f for the force frequency. We've seen that differential equations are easier to solve in exponential form, so we're going to write our forcing function as a complex exponential and just take the real part anytime we want to actually plot the graph or anything. So for the force equation then, it's going to be sum of the forces is the elastic force, the drag force minus CV, velocity is x dot, plus this applied force, and that's got to equal the mass times the acceleration. So we'll gather terms on the right hand side here. We'll leave this one by itself. Bringing these two over, we'll get mx double dot plus cx dot plus kx equals this complex exponential. We'll then divide through by mass and make the same substitutions that we did for the damped harmonic oscillator. And we end up with this differential equation here. After we divide through by mass, replace omega naught squared with k over m, and c over 2m is gamma, so this is twice gamma times x dot. So that is our differential equation. Now we're going to substitute an equation of the form e to the I omega ft. We're going to actually make this minus delta. So change that to a minus, please, just so it's consistent with what's going to follow. All right, now when we do that, we're going to, as per the differential equation, have to do a second derivative of that. So this is x double dot. So the first derivative is just going to bring down an I omega. The second derivative will bring down another I omega, so it'll be I squared omega squared. So when we substitute this in, we're going to get I squared omega f squared, which will just be negative omega squared, obviously, then times af e to the I, and then I'm just going to put that bracket there like that. Then plus twice gamma x dot is going to bring down a single I omega. And again, I'll just leave that bracket. Then we've got plus omega naught squared times x equals f naught over m e to the I omega ft. Now, these four exponential terms are not the same. These ones here have an omega ft term, but they also have a minus delta term in them. So if we expand those then, well, we'll make I squared minus 1. And we're going to get e to the I omega ft, and then e to the I times minus delta. Same thing here, it'll be e to the I omega ft, e to the I minus delta. Same thing here. And we see that we can cancel off now these e to the I omega ft terms. And because we've got 3 e to the minus I deltas, I'm just going to multiply both sides. So we're going to cancel e to the I omega ft, and we're going to multiply by e to the I delta. So on this side, the e to the I delta times e to the minus I delta gives e to the 0, which just gives 1. So that wipes out, that wipes out, that wipes out, and then we just pick up an e to the I delta on this side. So when we do that, the equation that results is minus omega f squared af, and that canceled, and that got changed to a 1, plus twice gamma I omega f, that canceled, that got changed to e to the 0, which is 1, plus omega naught squared a, that canceled, that got made into 1. And then on this side, we get F naught over M times e to the I delta, which I'm going to write as cos delta plus I sine delta. Now that's a whole lot of differential equation solving, but we've actually gotten somewhere now, because we can now just compare like terms. So we've already canceled this term out, and we've just used Euler's theorem here on this side. And now we're just going to gather the terms together. So first, if we compare the real terms, this one's real, and the cos delta term will be real. We'll gather those together and write them here. And then the imaginary terms, well, there's this one on the left side, and then the I sine delta on the right side. So comparing real terms and doing a bit of factoring, we're going to get omega naught squared minus omega f squared AF. That's the real terms on the left. That's got to equal F naught over M cos delta. That's the real term on the right. So that's the real equation. The imaginary equation is twice gamma omega F. That's the coefficient of I on this side, and the coefficient of I on this side is just going to be F naught over M sine delta. Okay, so that's the imaginary equation. I'm now just going to take the ratio. Oh, hold on, I missed the AF there. Let's go back, because this has an AF. Oh, I really missed it. Yeah, I missed it here too. There's a missing AF term right there. Isn't that special? So in this equation here, that AF should be there. So make sure you add in an AF here. That means we've got to add it in there. That's important, otherwise we're not going to get the correct result here. Because what I want to do now is take the ratio. Now when I take the ratio of this over this, F naught over M cancels, sine over cosine is going to give me tan delta, and I'm going to end up with all of this divided by all of this. So that's going to be twice gamma omega F AF over omega naught squared minus omega F squared AF, and the AF just cancels out. So that's then an expression for tan of delta. Now that boils down to a triangle, because tan is opposite over adjacent, so we can think of this as being twice gamma omega f on the opposite side, and then the adjacent side is omega naught squared minus omega f squared. That means our hypotenuse is the rather unfortunate, is going to be omega naught squared minus omega f squared squared, plus the square of this side is just 4 gamma squared omega f squared square rooted. So yes, that rather lovely expression. Okay, let's try and resurrect our triangle there. There we go, there's our hypotenuse. Now what that's useful for, of course, is now we can do sine and cosine. Because this would be the angle right down here, right? This is the delta angle. So let's substitute that triangle into our first equation. So we need to substitute in for cos of delta. Well, cos of delta just equals this, omega naught squared minus omega f squared, over this big ugly square root. So let's go back to our equation here, which was omega naught squared minus omega f squared AF is f naught over m cos delta. So now I want to substitute in for cos delta. Cos delta will be this divided by this this huge, monstrously ugly square root term. Well, then you see that this term cancels on both sides, and we can actually solve for AF. It's F naught over M divided by this big ugly square root expression here. And what is this? Well, remember, this is the amplitude of the solution, and you see that that depends on the force amplitude. Let's get this out of here, down to where it should be, right about there. So remember, we had tried a solution of the form AF e to the I omega ft minus delta, and we have now solved for AF. It must be this, and that's recopied a little bit more neatly here. And then the delta, the phase shift, is given by this expression here. Now we remember that omega naught is the natural frequency of the spring, that's root k over m. Omega f is simply the frequency of the forcing function. Gamma is c over 2m, all right? And we have now got a solution for this differential equation. But we remember, oh, we're not done yet. Oh, first of all, the real part of this equation would be AF times the cosine of this. Okay, so that's indicated right here. But we're still not done, unfortunately, because remember that this is a second order differential equation, and we need a second solution. Well, we've already solved this equation. We just did that. All we need to do, it turns out from the theory of differential equations, is add a solution to the homogeneous equation, which is what we got when the right-hand side was 0, and we did that last class for the forced damped harmonic oscillator. The reason that works, of course, is if you plug those two solutions and you plug in the solutions of those two differential equations in, then you're going to get, well, we're going to call the particular solution, this big nasty one over here, xp. So you'll get xp double dot, x homogeneous, that's the unforced one, double dot, etc., etc. So you do all those derivatives, and you can split that up, of course, into xp double dot plus twice gamma xp dot plus omega naught squared xp, and then x homogeneous double dot plus 2 gamma x homogeneous dot plus omega naught squared x homogeneous. Now all of this just equals 0, right? That's the definition of it being a homogeneous solution. And so you just end up with all of this, but we just showed that all of that has to equal F naught times, well, cos of omega ft, or e to the I omega ft. And so you see, adding the homogeneous solution, because the differentiation is just going to give 0, it will necessarily satisfy the differential equation, but then we've got the sort of two independent solutions that we need. So all of that goes to say that we just need to add the solution we got last time to the unforced oscillator, which is written here. So the general solution to the forced damped harmonic oscillator is this complicated expression here. This was the unforced damped oscillator from last time, and this is the equation that we just solved for, all right, where the amplitude F, AF, of the forced motion is this term here. And then, once again, I was making this minus delta. And then the delta is given by this arctangent expression right here.